We're in chapter 10, correlation and regression. 10.1 is on correlation. Correlation exists between two variables when the values of one variable are somehow associated with the values of another variable. This happens with most things like heights and weights. There's usually some kind of correlation between the two. Maybe the number of hours that you study in your GPA have another. What we'll be dealing with is linear correlation. This exists between two variables when there is a correlation and the plotted points of the paired data result in a pattern that can be approximated by a straight line. Scatter plots show these different types of relationships that we have. And the first two that we have on here, these are linear. And these other two that we have, or these other three, these are examples of non-linear or not linear. We will not be studying those kind of correlations in this class. We only deal with linear correlations. So those first two graphs that we have, you'll notice that one is rising and one is falling. The one that's rising has positive slope. The one that's falling has negative slope. So stuff from algebra. Positively associated is whenever the values of one variable increases, the value of the other variable increases. This is also considered positive slope for those of us from algebra. Negatively associated is where the values of one variable increases, the value of the other variable decreases, and we have negative slope. We have a linear correlation coefficient is a measure of strength and direction of the linear relationship between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and R represents the sample correlation coefficient. There is a crazy equation there that we will not have to stress about because we'll be getting our value of R, our correlation coefficient, from the calculator. So to find the correlation coefficient with a TI-83 and 84 calculator, input your data into L1 and L2. You're going to go to stat, to test, and to F. It's lin reg t test, and for you, if it's something else, change it so it matches what you have. A little different here with the calculator stuff, and the reason why is because there's so much information that is given. You're going to get a whole bunch of output, and we'll be referring back to this quite often. So this is what the input looks like. And this is what our output screen is going to look like. Again, you might have to scroll up and down just to be able to see everything. So input, if you notice, your X's are your L1, your Y's are your L2, frequency is set to 1. We will talk about rho, not equal to, less than, or greater than later. The regression equation later. But you're going to get out a few things here. But the one that we are talking about right now is the correlation coefficient, which is R. And that value will be different depending on the problem that you have. So properties of the linear correlation coefficient, there's some pictures to look at. Couple things. R is going to be in between 1 and -1. If R is equal to 1, then a perfectly positive linear relation exists between the variables. And if you look at that, we do have a picture of that over here, the last graph. You notice those points that we have, those data points make a perfectly straight line with positive slope. If R equals -1, then a perfect negative linear relation exists between the two variables. We don't have a perfectly negative in the pictures that we have, but we do have -0.90, and it's pretty close to -1, and those values, those points are looking pretty close to a perfectly straight line. So the closer R is to 1, the stronger the positive linear relation. The closer R is to -1, the stronger the negative linear correlation. The closer R is to 0, and we do have that up here also. So when R is 0, you'll notice that those points do not look anything like a line. They look more like stars in the sky. There's a little or no evidence of a linear relation between the variables. There could be a relation, but just not a linear one. So R is unitless, and R is very sensitive to outliers. How do we know if a correlation between two variables is strong enough to conclude that a linear relation exists? we calculate the critical values and compare it to the correlation coefficient. So we are going to have critical values and correlation coefficient. So testing for a linear relationship. So we have two different ways of calculating these. First one is going to be using your p-values. Your p-values, which we've done before, if it's less than or equal to alpha, supports the claim of a linear correlation. And if it's greater than, then does not support the claim. We'll get more into this later, but give that a star. Use table A6 to interpret your R values. So table A6 should be on the last page in your packet. And so this is, and if it's not, if you don't have it, you can easily look it up, and it's also in the textbook. But here's our critical values. This would be given to you guys on the exam for you to use. So going back to the notes. But that is, again, that's on the last page of the packet. So we're going to determine the absolute value. Remember, absolute value is going to make that value always positive of the correlation coefficient. So we need to find the absolute value of R. We need to find the critical value in table A6, which is in the back. And we're going to say if, so I'll give that a star, if the absolute value of R is greater than the critical value, then we say a linear relation exists between the two variables. Otherwise, no linear relation exists. So, example says listed below are the amounts of bills for dinner and the amount of bills, the tips that were associated with those. It says, is there sufficient evidence that there is a linear correlation between the bill amount and the tip amount? So first thing you guys need to do is enter in all these numbers, say L1 and L2. So pause the video and put those numbers in. Once you have those numbers in, we are going to go to Stat, to Test, and to, for me it was number F, or letter F, LinReg t-test. And with LinReg t-test, we're going to enter in all the information like we did up above. L1, L2, 1, and when we do this, I'm going to go ahead and instead of using the p-value method, because we've dealt with that quite often, I'm going to go ahead and look at R. And so you might have to scroll down a little bit, but once you get to R, let's round it 3 decimal places. I'm going to write down it should be 0.828. And then we also need to compare it to our critical value. So if you look at this data that we have in here, you guys will notice that we have 1, 2, 3, 4, 5, and 6 different bills and the tip amount that they gave. So when I go down to look at my value down here on my table, so going to A6, the last page in your notes, you'll notice that you have a value of n, and n is 6 right here. And for us, alpha is either going to be 0.05 or 0.01. I want you guys to use the significance level of 0.05. So the value of that we have for our critical value is going to be 0.811. So I'm going to go ahead and copy that down up above. So 0.811. So we have 0.811. And for this problem, it does not tell us what alpha is, so we'll go ahead and put down alpha is equal to 0.05. It should tell you normally. Okay, so we have to look at the absolute value of R, and the absolute value of 0.828 is just going to be the same value, so 0.828 is just equal to 0.828. And this is what compared to your critical value. This is greater than the critical value. And again, your critical value is 0.811. And because this is greater than, if you look back up here where we start, it says if absolute value of R is greater than the critical value, we can say that a linear relation exists between the two variables. So a linear relation exists between the two variables, which is going to be between the bill amount. And you would think that there would be, just because if your bill goes up, your tip should go up too. Bill amount and tip amount. So on to the next page. It says the data below is the ages of actresses and actors. And this problem I'm going to leave for us to do together during our mini lectures. The value of r squared is the proportion of variation in y that explained by the linear relationship between x and y. And there's an example here that we'll look at together. And then I gave you guys a starter. This is back from chapter 1 and 2. So do not forget, correlation does not imply causation. There's some common errors for you guys to also look at. And then we get into the actual formal hypothesis testing. So this is a formal hypothesis test to determine whether there is a significant linear correlation between the two variables. Use the following null and alternative hypotheses. So this is something that you definitely need to know. So H naught's going to be rho is equal to 0. There's no correlation. H1 rho does not equal 0. That means that there is a correlation. And we're going to go ahead and squeeze in one word in there. I'm going to put no linear correlation. And for this, it means that there is a linear, because we are only dealing with linear relationships or correlation. Okay, and then next thing on here, the test statistic, again, is given to you guys with the formula. We're not going to stress about it just because we use the calculator for that value. And there is another example on here that we will finish together during our mini lectures.